Hello, welcome to another tutorial in which we seek to solve, in this particular case, linear second order ordinary differential equations, but ones that have variable coefficients, or in this particular case, following on from the last video, I'm going to solve a similar problem, but one that has a change of sign, which makes the solution a little more complex to determine. So in my last video, I'll write this equation down. We solved y double prime minus x y prime plus y equal to 0. That is what we looked at in the last video. Now, all I'm going to do here is to change the sign there in front of the coefficient of x to plus, to a positive sign. But we're going to attempt to determine, first of all, a linearly independent solution. We have to, of course, use trial and error to do that, but this is a little more complex. We can't just choose y equals a constant or y equals c of x. Those are out in this particular case because what you will notice is that if you differentiate this twice and substitute back into that equation, well, we'll just quickly do it. We get y prime equals 0 and y double prime equals 0. So if we substitute all of that back into that equation, we get the left hand side is equal to 0 plus x times 0 plus plus a constant, which is equal to c. Now that clearly y equals c clearly does not solve this equation here, because we found that substituting y equals c in gives us c on the left hand side. That clearly isn't equal to 0, so it does this. Y equals c does not solve that equation. What about this one? So we've got y prime, if we just separate that with semicolons, we've got y prime equals c and y double prime equals 0. Now, in this particular case, we've got 0 plus x times c plus cx. And as you can see, we get cx plus cx, which is equal to 2cx. Once again, that clearly is not equal to 0. So this also does not solve this equation, which I think we will call equation 1. Okay? Now, I'm just going to erase the board because we have to find another linearly independent solution that does work. And I'm going to, because I just guessed this solution when I solved this equation, and it did happen to work. So we're going to try a solution, well, we'll just say try y equals ce to the minus x squared over 2. Because quite often, the reason why I chose this solution was because quite often these equations do seem to have the habit of involving exponentials to the power x squared, or minus x squared, or minus x squared over 2, or x squared over, and so on like that. So we're going to see if this works once we differentiate it twice in each case and substitute back in. Right, so okay, we've got y equals ce to the minus x squared over 2. Well, hopefully you should realise that the derivative of this is equal to y prime, and that is equal to, well, first of all, you have to differentiate this index. So that becomes 2x over 2, which is just x. And of course, we've got a minus sign. So we're going to have minus cx e to the minus x squared over 2 as the first derivative. Okay? Now we need to find y double prime. And it turns out if you differentiate this using the product rule, you get minus c e to the minus x squared over 2 plus x squared e to the minus x squared over 2. Right, so what does the left-hand side equate to? Well, we'll just write down the equation again. We've got y double prime plus x, y prime plus y equals 0. Okay? And in fact, we don't need to worry about that equals 0 at the moment. We need to prove that that is equal to 0 when we substitute all of these functions into this equation. So we know that y double prime is equal to all of this here. So we'll write that down. Minus c e to the minus x squared over 2 plus x squared e to the minus x squared over 2 plus x times, in brackets, this term here, because this is the y prime term. So we've got minus cx e to the minus x squared over 2, and we close the bracket, and then we've got plus y, which is ce to the minus x squared over 2 plus ce to the minus x squared over 2. Right, okay, what does this turn out to be? So that's the left hand side is equal to that. Well, we'll just tidy this up a little bit. So we've got minus ce to the minus x squared over 2. Make that 2 look a little bit clearer. Plus x squared e to the minus x squared over 2. And this time it's going to be minus cx squared e to the minus x squared over 2 plus ce to the minus x squared, whoops-a-daisy, x over 2, if you can see that. Let's make it look a little bit clearer. Okay, so what do we have? Is there anything that will cancel? Well, hopefully there is. So what we can see is that we've got two similar but opposite terms here. Which obviously cancel. And where's my trusty green pen? We'll use this one. And we've got, I don't think that's really a very bright and vibrant. We'll try and use this one. So, yes, that's a bit better. We've got this, actually it's plus x squared e to the minus x squared over 2, which is the same but opposite to that. And by the way, lo and behold, I have made a little mistake because there should be a C there and a C there. These are constants, of course. C is a constant there, there, and there. So there should be a constant there, and of course, if I just erase that a little and put the C in, then it becomes a little clearer that, yes, this cancels with this, and this cancels with this. So that is actually equal to 0. So therefore, this is one linearly independent solution. So we know that, you know, we're on the road to finding the general solution now. So I'll just erase this from the board and let us continue with using the Wronskian. Because that's what we did in the last video. That would be the best plan of campaign here. Actually, there is a simpler way to find a solution. And I'm tempted to show you it now. But I think we'll leave that until last. I will just continue with the Wronskian solution here. Because it's all very, very good practice for a start. So, the Wronskian, and you might have noticed in my last video regarding the equation where this was negative here. So y double prime minus x y prime plus y equals 0. In my last video, when I wrote down the Wronskian, I wrote down e to the minus integral of p dx. What I should have had in that video was another constant, which we'll call constant, well, I'm just going to call this C1. I know that's C, but I'm calling that C1. So the Wronskian should always have a C1 coefficient in front of the exponential. Now, if you remember back to my last video, I said that P is actually equal to this here, or in the previous video, P was equal to minus x. In this case, P is equal to plus x. So what do? Right, we substitute in the x for the P. So we've got e to the minus x dx. Right? And let me put a dividing line down. It's not a... There we are. So dividing line down there. So we leave a bit of space on the right hand side. So the Wronskian is equal to C1 e to the minus x squared over 2. So you just integrate x, you get x squared over 2, and the minus sign just stays where it is. So it's C1 e to the minus x squared over 2. Right, now we also have to find the determinant version of the Wronskian. I mean, that is actually the determinant, but we have to use a kind of a matrix determinant to form an ordinary differential equation with y2 in it, so that we can then solve for y2. So that's why this is important. So the determinant of version of the Wronskian is, well, the first term is y1, then we've got y1 prime, then we've got y2 and y2 prime there, yeah? Now, I think I can write this all on one line. We know that the first solution is ce to the minus x squared over 2. So we'll write that there. Let's just extend those modulus signs a little. There we are. And we know that the derivative of that is, oh, and that's, yeah, that's c. So we've got c x e to the minus x squared as the derivative of this function here. So differentiate that, you get that. And of course, y2 remains just as y2, and y2 prime remains just as y2 prime. Now, if you take the determinants of this, it's that first entry times the final fourth entry minus this third entry times the second entry. So what we have is the Wronskian is equal to CE to the minus x squared over 2 y2 prime. In fact, I like to write that for the purposes of what we're about to do next as dy2 by dx. Y prime equals dy by dx. Right? Now, we're subtracting this times this. Well, minus times a minus is a plus. And we've got cx e to the minus x squared over 2 y2. Right. Now, I think at this stage, I really should be writing the equation numbers down properly. So we're calling this first equation equation 1. This first solution is equation 2. The Wronskian is equation 3. And this determinant version of the Wronskian is equation 4. So, right. So if we equate equation 4, well, we could say we'll just keep it like this. If we equate equation 3 with equation 4, we obtain CE to the minus x squared over 2 dy2 by dx, just dx, plus cx e to the minus x squared over 2 y2, and that is equal to this c1 e to the minus x squared over 2. And you'll notice that I have a c1 in there now, whereas I didn't have a c1 in there in the previous video. It actually didn't affect the solution in that previous video, because when we divide through, we get a constant, different constant over another different constant here, which we can just call constant 3, like we did in that video, that previous video. So what we do is we can see that what we're effectively going to do is divide both sides of this equation, which we'll call equation 5, by CE to the minus x squared over 2. Otherwise, you could just say, well, that cancels with that, and that and with that. So everything cancels there, leaving you with a constant here, a cx there, constant times x there, and a constant there. So we can rewrite this as dy2, and I'm going to divide throughout by that constant. So we get dy2 by dx plus x y2 equal to c1 over c. But of course, like I said, you can just equate that C1 over C to C3, and I'm abbreviating it there. I'm effectively jumping a step there because I want to conserve space on my whiteboard. So we've got a nice first order ordinary differential equation here. And we can solve this via the usual method of finding an integrating factor. So an integrating factor is e to the power of the integral x d, oops, excuse me, making a little mistake there. You got to watch me, I do make mistakes and forget things and forget to put things in. E to the power of the integral x dx, because it's this x here that we have to substitute up there. A bit like using the Wronskian, except the Wronskian always has a negative sign in it. The integral sign doesn't, unless that term there happens to be negative. So if we integrate this, we get e to the x squared over 2. Right? Now, that means we multiply e to the x squared over 2 by the whole of this equation. So we've got e to the x squared over 2 dy2 by dx plus x e to the x squared over 2 y2, which is equal to C3 e to the x squared over 2. Okie doke. Let me just check that I'm on the right lines. I think so. So, as you might recall from the previous video, where that was minus instead of plus as it is here, we can easily write this in a more compact form. So we've got d by dx of something. And I'll just explain this a little better than perhaps I did last time. We know that one of the terms that we have to differentiate is y2. But what do we choose for the other term in the product? Is it x? Is it x e to the x squared over 2? Or is it just e to the power x squared over 2? Well, when you've got an ordinary differential equation, a first order ordinary differential equation in this form with the derivative to the far left of anything else, you know that after you've chosen y to be one of the factors that you're going to differentiate in the product, you know that the only other factor left is always this term here. So it's e to the x squared over 2. And of course, we'll just double check that. Differentiating the y2 and leaving that alone, we're left with e to the x squared over 2 dy2 by dx. And that's going to be plus, well, you're not going to differentiate the y2 in this case, but you are going to differentiate this, which comes out to be x e to the x squared over 2. So that, the derivative of this product is that, which is the left-hand side there. So we needn't go any further right at this very second, other than to write that left-hand side equal to C3 e to the x squared over 2. Right, so again, we're going to run into slight difficulties with the integral on this side because it's yet again another imaginary error function. But we'll deal with that when we come to it. First of all, it's easy to integrate the left-hand side, and so we write down e to the x squared over 2 y2 equal to c3 times the integral of e to the x squared over 2. Right, okay. And by the way, I think in the last video I might have forgotten to add on a constant of integration in that video, but it didn't really affect the final general solution because two of the constant the constant over here eventually morphs into part of the original first linearly independent solution. So you just add them together, but you still get the same solution. Anyway, so what we get here is e to the x squared over 2 y2 is equal to c3 times, once again, if I can write straight, times pi over 2 times I, the imaginary error function of x over the square root of 2. So I hope you can see that. Let's just but that's not, we're not there yet. Actually, as I said, there should be a fourth constant of integration. So we've got y2 equals, if we divide both sides by e to the x squared over 2, we're left with y2 on this side, and on this side we're left with c3e, and if I may just write that constant 4 there, we've got c3 e to the minus x squared over 2 plus c3, and I'm going to try and squeeze this on, pi, I don't think I'm going to be able to squeeze it on. Let's just make a little bit more room up here. So we've got y2 equals c3 e to the x squared over 2 times pi over 2 times the error function, or the imaginary error function of x over the square root of 2 plus c4 times e to the x squared over 2. Right, and I'll show you how this yeah, sorry, that should be minus, shouldn't it? If you divide both sides by e to the x squared over 2, you end up with a minus, an e to the minus x squared over 2 there, and an e to the minus x squared over 2. And now I'll show you how the general solution is formed and how that gets absorbed into the first linearly independent solution up here, which is equation 2. Right. So let me just Right. Okay. So we know that a general solution is formed by adding well, this would be y1, wouldn't it? We chose that as y1 by adding let's say equation 2 to equation, and we'll call this, I can't remember what equation we got up to now, but we'll just call this equation 6 for the sake of argument. So I'm calling it equation 6. There are probably about 4 equations or 5 equations down here. So I'm calling that equation 6. And of course, this means that y equals y1 plus y2. Right? So we've got y equals ce to the minus x squared over 2. That's that first linearly independent solution. And I'm going to write that down first. Plus c4 e to the minus x squared over 2 plus this c3 root pi over 2, and of course we don't want to forget, oh yeah, the exponential, minus x squared over 2 times the imaginary error function x over the root of 2. Right, now you might be able to see that this part of the solution can be factorised and simplified indeed. So we've got c plus c4 times e to the minus x squared over 2 plus c3 times the square root of pi over 2 e to the minus x squared over 2 times the imaginary error function x over root 2. Right? We can just call this a different constant, like, I don't know, constant 2 e to the minus x squared over 2 plus c3 times the square root, can't do my square roots very good these days, can I? Pi over 2 e to the minus x squared over 2 times the imaginary error function of x over the square root of 2. And I hope that you can see that last bit. I'll just go over it in slightly blacker ink. There we are. X over the square root of 2. So there we are, and that is our general solution to that equation. So you can see in this particular case we had to I didn't go through a whole range of potential solutions to try in that equation, but it turned out that, you know, our first guess was correct as a first linearly independent solution, and we then used the Wronskian method, both the determinant version of the Wronskian method and its counterpart, which is also a determinant but an straight off exponential function. We equated those, and then we proceeded to solve the first order ordinary differential equation to get the second solution y2, and then we've added this second solution y2 to the original solution y1, and finally we find that this is the general solution. So I hope that has been helpful to you, and again, as I said before, that I hope that you will come back to watch more videos and watch any that you haven't already seen, that are already up there on YouTube, and I'll bid you farewell for now, but see you soon.